In this video, we're going to talk about propositional equivalences. Specifically, what we're looking at is this idea that two things are equivalent. Now, equivalent often makes people think equal, but it doesn't necessarily mean equal. It means that the same result kind of happens, and it can kind of go about a couple different ways. For instance, my favorite example of two things being equivalent is saying that 1/2 is the same thing as 3/6. That's true. I mean, we know that we can even reduce 3/6 to equal 1/2. But if I were to draw a picture to represent these two fractions, the pictures would look different in terms of the basic setup, though the same amount would end up being represented by each. They're equivalent, even though we sometimes call them equal. Okay. But we kind of need to make a distinction here because we definitely have things that are going to look different. Before we get into equivalences, we need to understand a couple concepts. The first is a tautology. So a tautology is a proposition which is always true. All right. So an example would be, let's find P or not P, right? That's what this first example is, P or not P. So I'm going to do the truth table for it. So P is, we just do true and false. Not P is going to be the exact opposite. So false and true. And then since or always takes on true whenever true is available, both of these come out true. So that's what makes it a tautology. The truth table has all true values. Okay, oops. So this is all true values, but I'm not going to say that, just they're all true. Okay. A contradiction is when it's always false. So let's try this, an and statement. So same basic setup. We start with true or false for P, and then the not P is going to be the opposite, false or true. So and takes on false whenever false is available. So when we have this is going to come out false, and that's going to come out false. So this is a contradiction because everything came out false. A contingency doesn't come out either way, all true or all false. In other words, it's just not a tautology or a contradiction. So here's an example of a contingency. So let's do this truth table. So this is going to be true, true, false, false. Q is going to be true, false, true, false. Okay, not Q. We're going to switch them around for Q. So this is going to be false, true, false, true. And then or, we're going to do or for P and not Q. So we're looking at this column and this column. And since it's or, it's going to take true whenever true is available. So this one's going to be true, true. Okay, this doesn't have any true available, so it's got to be false and then true. And this is called a contingency because it's not a tautology or a contradiction. I'll go ahead and erase all this highlighter. It's not necessary. And wow, I did a lot of highlighting, didn't I? All right, that's fine. Cool. Moving on. So logically equivalent is when this statement is a tautology. What it really means is that their truth tables give the same values. In fact, it's stated right down here. Two compound propositions are equivalent if and only if the columns in a truth table giving their truth values agree, meaning the same exact values. So let's look at an example of that. Let's show that these two things are equivalent. All right. So what we're doing is we're comparing this to this. And you see I have them both here in the table. So I'm going to compare their truth values. And if they come out the same, they're equivalent. Okay, so let's go ahead and start this. So this will be true, true, false, false. Q is true, false, true, false. Not P is false, false, true, true. Okay, so I'm going to start with the first column here. So not P and Q. So that's using these two. I'm going to erase that just so I see. Okay, so I'm using those two. Okay, so since it's or, it's going to take on true if it can. So this one's true, this one's false, this one's true, this one's true. Cool. All right. Now this is asking us to do if P then Q. Okay, so now we're comparing the first two, and it's going to look like the if P then Q table that we did previously. So with this one, there's only one case that's false. That's when we start with true and end with false. So this one's true. Here's that case, that's false. We start with a true statement, end with a false statement. This one's true because you can start with a false statement, and that's fine. Okay, so now I'm going to compare the answers. Oops, sorry, got a little too vigorous with the eraser there. Okay, and these two truth tables came the same, so they are equivalent. Yay, because they're the same. All right, so that's how we show equivalence. We can just go through their truth tables and show that they come out the same. Okay, De Morgan's law is something we'll refer to quite frequently. And really what I kind of like to think of it is almost like a distribution. It's like we take this not symbol and we distribute it. But when we do that, it changes the and to or. And it kind of does that over here too, right? It almost distributes it and then it changes the or to and. So De Morgan's law almost works like distribution. And here, let me write that down. Works kind of like distribution. All right. Let's go ahead and show that these are equivalent. Now they're referring to the second law. That's this one. So this is the first one. Oops. I'm so sorry. I'm sorry. I bumped the pad and it got mad at me. So that's the first one. That's the second one. So we're going to show the second one is equivalent. Okay. So I'm going to kind of show you how we build the truth table to do that. So first thing we need is on the left side, we need to find P or Q in parentheses. So I'm going to start with that, P or Q. And then I'm going to find not P or Q. And that'll show the left side. Okay. Then on the right side, I need to find not P, not Q, and then I'm going to find not P and not Q. All right. So these two this column here and this column here, those are the two we're comparing. So we want those two to match in order for them to be equivalent. Okay. So here, let's start with the beginning. So P, we'll start with true, true, false, false, always. Q will do true, false, true, false. Okay, so P or Q, it assumes true whenever possible. So all of these are true until the last one, which is false. Okay, now for the not, we're just going to switch all these values. So it's going to go false, 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 true. Okay, so this is a contingency, right? Because it's not a tautology or a contradiction. Cool. Okay, not P. So we're going to change the first column. All right, we're looking over here at the first column. I'm just going to highlight it so I'm remembering. Okay, so this is going to be false, false, true, true. And then we're going to look at Q for this one. So this is going to be false, true, false, true. Cool. Now we're going to look at these two right here to look at this. All right. So because it's and always does false when false is available. So false, 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 true. All right. So now that we're done, let's compare the two columns of interest. That was this one and this one. This one is the left hand side, and this is the right hand side up here. I'm talking about up here in this statement. And they match. Boom. They're equivalent. Oops, there's the happy face. All right. Let's try. Oh, okay. Before we try another one. So the textbook has a bunch of logical equivalences that they've summed up into some tables. And I went ahead and pulled them into the notes just so you can have them to refer to when you're working on homework. We're going to go through some of them. You don't have to memorize them. And I'm not going to make you memorize them, I don't believe, for the exam. I'll make a decision on that. I don't think so. But I did want to pull them in here just so you could kind of look at them. And it kind of makes sense when you kind of go through the left ones, like looking here, if you do P and true, of course, that ends up being whatever P ends up being, okay? Because if you're pairing an and statement, and always takes on false. So if P happens to be true, the whole thing is true. If P happens to be false, the whole thing happens to be false. So you can kind of reason your way through why they make sense, all right? They have all of these, and then they have De Morgan's law too. They are including De Morgan's law right here, which we just talked about. And then they even have some more additional statements down here on conditions and biconditional. We're going to kind of pull through some of them. Some of them are actually homework problems. And actually, I think I saved one. Yes. So we're going to show that this statement is logically equivalent to this statement. And is this one of them? I thought maybe it was. Oh, there we go. Sorry, the table's not loading. Oh, okay, it isn't. That's all right. But the steps I'm going to show for this are going to be similar to what you would do in the homework. So I'm going to show that these two are logically equivalent. And I decided to build the table for you, just so you could kind of see if you're doing this by hand on the homework. All right. Wow, that's a terrible vertical line. I'm going to just try one more time and see if I can make it nice. Okay. So I have P and Q. So P, Q. Okay. So I'm going to start with this statement first. I think that's easy because it's just a little bit quicker. So I'm going to do not P and then not Q. And then I'm going to show not P and not Q. All right. Then to do this one, I'm going to need, okay. So here, I need this right here. Now I already have not P, so I need to do not P and Q. Not P and Q. Then I need to pair it with P or not P and Q. Then I'm going to take the not of that statement. So not P or not P and Q. Wow. Okay. Squeezed it in. There we go. So this is the right. This one right here. And here's showing the left. Okay. So let's go through the truth table. So true, true, false, false. All right. And this is going to be true, false, true, false. Okay. Not P is false, false, true, true. Not Q, false, true, false, true. And by the way, I'd encourage you to pause the video and kind of try to fill it out yourself real quick. See if you can do it and then compare to my answer. I know I tend to kind of go through it a little quicker. So maybe if you give it a shot and try and then see what I do if you get stuck, it might be a good way to kind of practice. Okay, so here we are comparing these two. True. All right. Now I'm going to compare not P with Q. And it's and again. So it'll assume false if possible. So false, 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 false. Okay, so the whole thing came out false on that one. All right. Oh, wait, I just realized. I'm so sorry. I thought that was kind of weird. I just compared the wrong two ones. Okay, so that's P, not Q. Oops. So these are the two. Ooh, there we go. Those are the two we want to compare. Okay, so false, false, true, false. Okay, cool. Now we're going to pair what we just did, this, with this. And that's going to give us this. Okay. So, or this time, or assumes true, if true is an option. So true, 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 false. Okay, now to do the last column, I'm going to switch all of these because all I do is have the not in front. So false, 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 true. And I'm going to compare this answer, the left one, the left one to the right one, and they are the same. So they are logically equivalent. And there you go.